Hello, my name is Tom Sal Thomas, and this is my lab report of Lab 3. On this slide is the table of contents and the order which I'll be going over my lab report. Introduction. The purpose of this lab was to find the correlation between the magnetic field of a barring magnet and the observable distance, both on and off axis, and to gain a better understanding of the Biot-Savart law in order to utilize it to determine the dipole moment of the barring magnet. So some important info is the Biot-Savart law and that the magnetic dipole is represented as the barring magnet in this lab. The magnetic dipole moment was found to be 2.81 amps times meter squared, and N, a constant, was found to be negative 2.9589. Some important concepts in this lab was that the barring magnet is representative of a magnetic dipole. The Biot-Savart law of a magnetic dipole is displayed in the slide. The relation between the distance dependence and magnetic field is shown with the B bar equal to K R to the N. K and N are both concepts. And in order to graph it, we have to linearize that. And when we linearize that, we have the natural log of the magnetic exponent of the magnetic field is equal to the natural log of K plus N times the natural log of R. Another information we need to know is that the magnetic field on axis is twice as strong as perpendicular, and the magnetic field on axis is equal to the mu dot over 4 pi times 2 times the dipole moment, which is equal to the area times current over z cubed, which z is equal to r, the distance away from the barring magnet. The materials required for this lab was a barring magnet, 2m6, a smartphone with a magnetometer map, tape, and an associated Excel spreadsheet. In this lab, the barring magnet is the system. Directions. Align the phone with the magnetic north so that Earth's field doesn't affect readings. Put 1 meter stick underneath it and make sure the barring magnet is at the end. Take 3 different measurements at one location and then switch locations and repeat this process 4 more times. This is the measurements for the on-axis magnetic field. For the off-axis magnetic field, add another meter stick that perpendicularly bisects the other one. Make sure the vertical and horizontal distance from the magnet are the same from the phone, and take 3 more measurements. The graph of the data is shown to the right, as well as the equation, with negative 2.9589 being n and negative 14.39 being natural log of k. From the line equation, we found that k is equal to 5.63 e to the negative 7 and that n is equal to negative 2.9859. We know that the magnetic field is equal to KRN from the distance dependence formula, and we also know it's equal to mu naught over 4 pi times 2 times the dipole moment over z cubed, which is the same thing as r cubed. So we can set those two equal to each other to get the magnetic dipole moment, with the equation being shown on screen. And we found that the magnetic dipole moment was 2.185 amps times meter squared. Some observations were, when the magnetic field is far away from the magnetic dipole, it is near zero. The closer the point is to the magnetic dipole, the stronger the magnetic field. As the magnetometer moved closer to the magnetic field increased, which is supported by the data on the right. This here is the code I used for my simulated model. And here is the actual results, where we have the simulation of the lab. We have the 4 perpendicular on-axis locations, as well as 2 on-axis locations, and the vectors there are representative of the magnetic field. And the purple one is representative of a 45-degree off-axis magnetic field location. When we used the experimental data, we found that the magnetic field at the 45-degree angle was 6.316 e to the negative 5 Tesla, whereas in the simulation it was 1.021 e to the negative 5 Tesla. So there's a discrepancy between the simulated and experimental, and that could be due to there was no z component in the simulated magnetic field, whereas there was a z component in the experimental magnetic field. Some errors were that could have been some interference from nearby magnetic fields. The surface I was using wasn't completely flat, and the phone placement was kind of inconsistent as well. To answer the first question, the x component measurements would be different, as magnetic north would affect it, and y component measurements would also be different / wrong, as magnetic north wouldn't be accounted for. And to answer the second discussion question, the direction of the magnetic the magnetic field would be the same. However, the magnitude of the magnetic field would double due to another magnet end to end being connected right to it.